or rather I should say good afternoon, everyone. Thank you for making to this meeting. We are Parklane. We are acoustic noise mitigation solution provider. All right, just wanted to go through the slides first, and then I'm sure at some point we will be talking about our the presenters. Okay. Key considerations when designing mechanical sound attenuation for exterior rooftop equipment. So this slideshow is targeted towards providing a solution as to what we would do when there's a rooftop equipment and how do we go about mitigating that. It's a quick presentation summary, what we will be covering, a quick intro of ourselves, and then basics of acoustics, and then talking about different output criteria. How do you go about setting a criteria for different noise sources, and what kind of mitigation can be applied towards it. And we also have some example slides of what we have done in the past. So key takeaways, as we talked about, is you'll get a little bit of what acoustics is, and then what type of rooftop equipment noise controls that we have, and different type of control strategy, what goes into designing a rooftop noise control. All right, so here we have the presenters are Matt Downey. He's the president of Parklane. Parklane has two divisions, one in United States, which is Parklane Solutions, and the other one is Parklane Mechanical, which is located in Oakville, Ontario in Canada. And myself, I'm Jagannath, and I go by Jag. I'm the US engineering lead, technical lead. So I will go over through the presentation right now. Okay, let's start with the acoustics. So I just want to give you a brief summary of acoustics rather than going into too much detail and giving you a lecture of the entire, giving you a lecture of what will happen, of what acoustics is. So sound waves. So sound is a pressure wave created by vibrating objects. There are some key aspects about sound that you need to know. One is that it is a longitudinal wave and that it needs a media to transmit. Some of the illustrations here show an example of how sound is transmitted. You have a tuning fork. When it vibrates, it vibrates the air around it, and the air transmits the sound, which is in a sense pressure wave, is being heard by a receiver. A classic example of, I'm sure most of you would have experienced this, where you have two persons talking over a piece of string and a cup. And that concept works because the sound transmits through different media. It doesn't have to be air. It could be liquid. It could be solids or whatever. And obviously, based on the media property, the sound transmission is also different. You should be thankful that the space is a vacuum, or you'll be hearing a lot of swishing and swashing of all those asteroids going around our planet. Now, just wanted to talk about amplitude and the properties of sound here. Sound, as I mentioned, is a wave, and just want to touch on some of the key aspects. In a typical wave, crest is the highest part, and the trough is the lowest part. A wavelength is defined by the space between two crests or two troughs, whereas the amplitude is the level of, in this case, how loud the sound is. In here, the illustration shows an example, classic example of a common equipment that you would have, you would have seen in a day-to-day life, and how much of noise that they produce. As you can see, a typical urban residence would be about 50 dB, whereas if you were in an airport, I'm hearing a jet taking off, it's about 130 dB. Now, before I go any deeper, I want to talk about this, the range of the sound. So human hearing can be, you can hear between 20 micropascals and 100 million micropascals. 20 micropascal is so small, which only tells you that it takes very little energy to create sound. Whereas this range between 20 and 100 million, that's a pretty big range. To put that all in a small scale, typically we represent that in logarithmic scale. And that's why you see most of the sound information in logarithmic scale. And the common unit that we use is decibels. All right, frequency. Now, frequency is the number of complete oscillations per second, as we talked about in the wave. It's a complete oscillation would be, just tracing through this, it's one sine wave. So in a second, how many of these waves can be made? And that's a frequency. A human ear can hear between 20 hertz and 20,000 hertz. And a common industrial noise then ranges between 25 and 10,000 hertz, and hence the human can, typically hear that. A wavelength is defined by the velocity of sound divided by the frequency. As you can see, the higher the frequency, the lower the wavelength, or longer the wavelength. Sorry, higher the frequency, the shorter the wavelength, and smaller the frequency, the longer the wavelength, which is represented here. Long wavelengths, high frequency, low frequency. Why is this important? Because when you talk about sound, you just define that in an overall broadband noise, but really it needs to be distributed in different frequencies, because it is key to know how the sound spectra is distributed so that you can mitigate it accordingly. Mitigation for a lower frequency is different from that of a higher frequency, and you'll see that later shortly. All right, octave bands. Now, like I was mentioning earlier, a sound, overall sound can be distributed in multiple bands, and typically defined in industrial standards between 0 band number and 8 band number, which represents each of these mid-band frequencies. Now, why is it so important that we have it in octave bands? In most jurisdictions, it is common that the noise limit will be, a limit to a certain overall noise level. And so why are we providing so much importance to the octave bands? It's because the noise cannot, mitigation of this noise, it depends on which frequency the noise is really dominant. And in this case, let's say, just as an example, this illustration shows different noise levels in different octave bands. The 250 hertz here shows a higher noise level in comparison to the other ones. So a mitigation for this will be different from if the noise level in 63 hertz were higher. Now, in the next slide, you'll see a common performance of a typical silencer. So this is a typical silencer performance. And you can see that, obviously this is an example. So a silencer performance can be higher or lower, but the curve is typically in this fashion, which means that it normally is more effective in the mid-band frequencies as opposed to the lower and the higher frequencies. In those instances, if the dominant frequency were in the lower frequency, then your mitigation would be something else and something different. It could be an unconventional method of mitigating them. It won't be a silencer. Same thing with a very high frequency. If you need it to be mitigated, it could be a silencer, but it could be a different style of silencer. So that's why it's so important that we know what the noise levels are at different octave bands. Now, weighted sound. So let's say you're measuring sound with a microphone. So whatever you measure out of a microphone, the data that comes out of it is typically in a linear scale, which is whatever the actual sound is. And it's represented in a Z weighted scale, which is not really weighted. So it's just called Z scale or linear scale. Whereas when a human ear, which is a sensor, when you can hear this sound, it will not be the same as what you actually measured. And the curve in red, which is called the A-weighted scale, is a very fair representation of what a human ear can actually perceive. So in the lower frequencies, you don't really hear a lot of the high amplitude sound in the low frequencies. And that's just the property of your ear, the way it works. sometimes you would have an occasion, even though the sound in the lower frequency is not loud enough for you to hear, your body can still perceive it through various different ways, vibration and whatnot. And in those instances, they would use something called a C weighted scale. These are the two common weighted scales that are used in the industrial practice. I just wanted to, give you a brief pointer on that. Now let's talk about sound power and sound pressure. Sound power essentially is the acoustic energy coming out of a source, whatever the source of the sound is. In this illustration, it's a good example here, a rooftop unit, that's the source of sound. So the sound power is essentially whatever the energy coming out of that source. So represented by LW, that's the sound power, 85. The units are the same for sound power, actually not the same. Sound power is represented in watts, and the sound pressure is a pressure, so a Newton per meter square. But when you put that in sound scale, it's always dB. As for sound pressure is just a portion of that acoustic energy measured, a certain distance away from the source. So as an example, if you were to measure 3 feet from this source, what that sound level will be. So if the sound power is 90 dBA, then if you're measuring 3 feet from it, it's, let's say, 85 dBA, because some of that is getting absorbed by the air or by the skin of the equipment. Or 100 feet, the reduction would be more significant because there's more absorption and more dispersion of the sound. A very fair analogy for this would be that of a bulb light. The sound power would be the wattage of what that bulb is, whereas the sound pressure would be whatever the lumens that's been measured or perceived by a person at an X distance from the bulb. Okay, so we talked about sound, having a very broad range and hence represented in logarithmic scale. Now, what happens if you have two noise sources that are fairly similar noise levels, as shown in the illustration, 70 dBA and 70 dBA, two noise sources? What will happen if you add them? It's not 140 dB. It's because it's logarithmic scale, mathematically that adds up to 73 dB. What this tells you is that for every 3 dB increase, the sound level is actually double. So as another example, let's say if there's 4.8 dB increase in the noise level, then it means that the sound level has been tripled, and so on and so forth. You can see that in the graph as well. Another key pointer is something called an acoustic masking. What that means is an acoustic masking is that, let's say there are two noise sources, one at 70 dB and another one is 80 dB. Then in this case, the dominant source, which is the 80 dB, is too dominant that the one that's less dominant doesn't really doesn't really impact the environment. So in this case, the overall noise level is 80. And this is only because that it's 10 dBs apart. All right, let's move on. Sound transmission. There are various means of sound transmission. And in this case, this rooftop unit has, as described here, path A, B, C, and D, different ways of transmitting. Typically, rooftop units, since they're on the rooftop, they impact the penthouse units, which is most likely the expensive units, and the neighbors that are facing this equipment or nearby this equipment. So what are the different ways of transmission? So it could be through the the floor, through that structure and underneath, and it could get into the penthouse unit. That's referred to here in the red arrows. And mind you, they are omnidirectional. I just represent by 2 or 3 arrows, but really they are omnidirectional, and they can be transmitted through various media as long as they have a media. And intake noise, even though this is one equipment, there are really multiple pieces within the equipment, multiple sources within the equipment. For instance, the intake, the noise is really dictated by the compressor unit that's very close to the intake opening, whereas the exhaust noise is dictated by the noise that's coming from the condenser fans. or exhaust fans. And the other means of transmission is through the casing itself. Sometimes the casing can be, or whatever the equipment is inside, is too loud that it not only comes through the intake and exhaust, but also through the casing. And in this case, all of this is important because mitigation depends on what part of this equipment is actually producing the noise and how do you go about mitigating it. When we talk about sound transmission, there are various ways that it gets transmitted, and here I talk about 5 of them, but really I want to focus on the 3 because this is the most common aspect. When sound hits let's say in this example there's a wall, an acoustic wall. So when the sound hits the wall, it could get reflected, it could get absorbed, and it could get transmitted. Now, more absorption is better because you want the sound to be absorbed rather than bouncing back and forth in and around inside this space. Diffraction and scattered are also other means of transmission. The diffraction is common in the case of an acoustic barrier where the sound typically just goes around the wall, but the amount of that is very minimal, whereas the scattering is simply a property of the surface of the wall that it's impacting. Now, I just wanted to also talk about transmission loss and insertion loss. This is a common terminology that you would be familiar with because an acoustic consultant would give that in his or her report. And what a transmission loss is defined by the noise reduction between the source and the receiver. Let's look at this illustration, for instance, where we have a source, a person talking, and the receiver, which is a person listening, has a wall in between them, but there's microphones on each end. So the reduction is really what you measure on the source end minus what you measure on the receiver end. That's a transmission loss. Whereas in the case of an insertion loss, it's a noise measured at the same location, but with and without an mitigation in place. So you can see the illustration below. It shows a person talking through a duct, but the microphone is only on the receiving end. And the insertion loss is essentially the difference between the one without the attenuator and one with the attenuator. All right, so let's talk about defining the output criteria. In this case, we have, obviously, we talked about the basics of acoustics. Now we need to talk about how do we go about setting a criteria. So what needs to be met and all that. As probably many of you know, it's dictated by the local bylaws. It could be a city, it could be a municipality, or even the state. And there are various ways of going about mitigating them. And as an example, it could be a silencer, it could be an enclosure, or even a barrier wall. And what is it that we need to specify these is the insertion loss or transmission loss. And also sometimes the means of mitigation will be dictated by the acoustic consultant, depending on what the source noise is. And as a noise solution provider, we make sure that that insertion loss is met based on whatever silencer that we design. It's a lab tested data that we provide, which would be in comparison to whatever the insertion losses or the transmission losses are. So I want to briefly touch on the acoustic modeling part of it, even though this is not something that that acoustic solution provider would do. It's an acoustic consultant that does this. I want to talk about it briefly so that you understand what is the process that happens before an acoustic solution provider such as ourselves get to work on this problem. So here is an example of a medical facility where there are multiple rooftop unit noise sources, but we're just really looking at one noise source here, but there are multiple noise sources. But the criteria is defined, again, it could be a local bylaw that you have to meet a certain noise level at the property line of the nearest residence. In that case, you are trying to mitigate whatever the noise is measured needs to be mitigated enough that the noise level at the property line of the nearest residence is not as much. All right. And then they take all the information, all the noise sources that they measured on site, and they'll put it in a acoustic modeling. And then they will, the model will spit out the information of how much of noise is being distributed all around the neighborhood. And it will also tell you what the noise levels, expected noise levels are at the neighborhood. Based on what the noise levels are and what the noise sources are, the mitigation type will differ. For instance, it could be an acoustic barrier, but all that criteria needs to come from an acoustic consultant, especially when there are multiple sources, so that all criteria is met at each individual receiver location. And so, like I mentioned before, common output specifications are dynamic insertion loss. And typically, this is what you would need if the mitigation method is silencer or an acoustic louver. A transmission loss when you want to put an acoustic enclosure around it. Also the case with the acoustic barriers. But typically, when they're acoustic barriers, they would have something called an NRC rating or a sound transmission class rating. It could even be phase density of the wall, or it could be SDC rating, like mentioned here. The graph shown here is an example of how the noise level or the insertion losses will be provided to a noise solution provider. It would be in the octave bands typically. In some instances, it could even be in the 1/3 octave band, which are even smaller bands. Now, I know we talked about this before. One equipment could have multiple noise sources. In the case of an exhaust stack, you would just consider this as a point source and then mitigate it as such, because it's the same noise that's coming out through a different direction. Whereas in this case, a rooftop unit has multiple sources of noise. As I mentioned before, condensing unit or the compressors can create noise, and typically because of their proximity to the intake, the noise from there is, the intake noise is dominated by the compressor noise, whereas for the exhaust, it's dominated by the exhaust fans. This is a classic example of different type of units and what ranges the noise, what frequency range do the noise typically occur at. And within a single rooftop unit, you could have multiple of these items that could be creating a broadband noise and having a noise level in different types of frequencies. As I mentioned earlier on, with different frequencies, the type of mitigation will differ to make it more effective. So it's key to know which octave bands are the noise levels at. Other key considerations. You'd be surprised that, in an acoustic mitigation, really, it's not just the acoustics that you have to consider, but there are other items that needs to be considered. And most of the time, the other items are more stringent and they may have more constraints. Let's go over that shortly. For instance, mechanical equipment. So in this case, the mechanical consideration that you would have to do is you have a rooftop equipment. Now, let's say the acoustic consultant has provided an insertion loss to be met, or even a transmission loss to be met. Then one can go about providing a solution by either putting a silencer on the top of the unit or have an acoustic barrier for mitigating the intake noise. But really, what needs to be considered is when you put the silencer in there on top of the unit, you're creating a back pressure for the flow coming out through the exhaust, and that will impact the performance of the equipment. So you need to be cognizant of the fact that whatever unit that goes on top does not impact too much, does not create too much back pressure. So that's one of the primary things that one would have to do when they design an acoustic solution. And not just that, when you put an acoustic barrier wall, you don't want to be too close so that the air for the intake is not sufficient gap for it to absorb, or else it could potentially create a recirculation problem. So all of that needs to be considered when you're creating an acoustic solution. One of the key aspects, especially for the rooftop unit, is a structural aspect. So when let's say you have a rooftop equipment and that needs to be mitigated. Whatever the solution that we come up with, it will have a certain wind load associated with that. And if it is in a high-rise building, you'll have a higher wind load. Typically, you would want to design it to hurricane wind forces so that it doesn't just fly off the roof. And it's not just that, you also need to make sure that this dead load, snow load, all of that is being accounted for. And when you do that, and if it is for an old building, you want to make sure that the building can actually withstand that additional load that's that's going onto the building. So that's a very key aspect. Typically you wouldn't have structural drawings associated with that because it's an old building, in which case you would have to do a structural study just to make sure that the existing structure can actually withstand the additional load that's been imparted onto it. In most instances, the solution that's provided for the rooftop units, can be connected directly to the roof. But in some instances, if for some reason the client doesn't want that, then we could also provide other options, something called a gravity barrier, where whatever the equipment is, it will just stay on top of the ground and still be able to meet all the required hurricane loads and all that stuff. So aside from mechanical and structural, you also need to make sure that constructability and operations is all accounted for. Now, in terms of constructability, you need to think about what size. Let's say you are making a barrier wall, or let's talk about a barrier wall here. So this barrier wall that's being built on top of a building, it's a pretty big size. Before you make them, you need to make sure that whatever size you make needs to be, typically the structures are all hot dip galvanized, so the size is so that it fits the tank. And during transport, it doesn't have any hindrance. You don't have to have it wide load and, or like a police escort. So you make sure that all of that is accounted for. And aside from that, you also need to make sure when it's being installed, where can you actually put down a crane and hoist this thing up on the roof. If it's a busy part of the town, then you need to make sure that you have proper permits to close down the road, and the right means to be able to hoist them up without taking too much time. So that typically cranes can be very expensive, so you need to be careful about that. So yeah, those are some of the other considerations that you would want to do. Here's a good example of what kind of the type of crane that's required will totally depend on where the location of these units are. Could be closer to the building, in which case you wouldn't need such a big crane to hoist it up. But if it were somewhere in the middle, then you will probably need something bigger so that you can reach out further. All right. In some instances, the solution doesn't even need to be acoustic. It could just be aesthetic. You have a rooftop equipment, and then you don't want this rooftop equipment to be the line of sight of a viewer. This could be dictated by some local bylaws. Could be a city, could be municipality, or whatever. In that instance, again, you're providing a louvered facade, or just a a facade. It doesn't have to be acoustic, but it's that's also something that typically can be provided. Can be acoustic as well. All right, so just want to debrief on key scope of items and who actually does this. For instance, the acoustic analysis, the first item that we talked about, typically done by an acoustic consultant. And then the mechanical analysis, which is conducted to make sure that the equipment can actually achieve that, as conducted by the mechanical engineer. Except for the first item, typically most of the other items are conducted by the solutions provider, such as ourselves. And the structural analysis, in this case, again, by a specific structural engineer, could be state to state because of these, the structural stamp that you would need for the engineering design. And then aesthetic review, again, could be done by an architect. Architect could come up and say, hey, you need something that's doesn't show this rooftop unit, so that could need some sort of screen. Could be a louvered facade. It could be a wall. So that would be by an architect. And then noise control supplier is coming up with a solution with what noise control is. And then obviously fabrication or noise control supplier will be the ones who are constructing it, and then installing could also be the noise control supplier, or the client could also have their own means of installing it on their property. So in summary, I just want to reiterate that it's very important that we have the output criteria to set up the acoustic requirements. The acoustic site modeling is important when you have multiple noise sources. You need to make sure that they're all addressed. Some noise sources, may not be loud enough that it's actually contributing to overall noise levels. So you just, the acoustic modeling will really help with that, identifying the key sources that needs to be mitigated and how much they need to be mitigated, and even sometimes how they need to be mitigated. These are some of the items that acoustic consultants typically provide, and they're very useful. Establish mechanical design requirements and limitations. It's not just mechanical; it could be structural, could be any other design considerations that need to be that needs to happen before one comes up with a noise control solution. So, like in the case of structure, we will have to conduct a base building structural review, which is typical if you have loads transferring into the building. So those are some of the items. Essentially, it's just a summary of what we covered earlier. So let's move on to the next slide. All right, so I just want to give you a brief introduction about Parklane and what we do. It's Parklane Mechanical is a family-owned business. As I mentioned, it is located in Oakville, Ontario. It has been operating for over 25 years, almost 30 come next year. We also provide vibration solutions, partnered with Mason Industries. Aside from Parklane Mechanical located in Oakville, we also have a division in the United States, Parklane Solutions, so that we can better service the clients in the United States. What are the different types of mitigation that we provide? It's not just limited to enclosures, silencers. We do custom mitigation depending on whatever the noise sources for each individual site. Not every rooftop will have to be mitigated the same way. They all have different limitations and different criteria. So they will potentially have different means of no two rooftops units will be mitigated the same way, is all I'm trying to say. All right, so the different types, we have enclosures, silencers, a circular silencer over chimney or a stack. We have enclosures which allow for intake and exhaust with acoustic louvers and whatnot. Some examples that we have done in the past for rooftop units. So in this case, there's a rooftop unit that required mitigation and the receiver is on the other side, and that's why the acoustic barrier wall is just two-sided as opposed to four-sided, because the receiver is on the other side. And in this instance, this is the example of an acoustic gravity barrier. The client preferred not to have the acoustic wall penetrating the roof, so it was provided in a way that it would just sit on ballasts, and it will still meet all the hurricane wind forces or other wind loads that are being dictated by the local bylaw. And we could also make the facade aesthetic looking depending on what the requirements are. So another way of mitigating a rooftop unit is not just by barrier wall. Sometimes the exhaust noise is loud enough that you would it will require you to put a silencer on it. So in this case, there's an elbow silencer and a acoustic barrier around it. Again, you don't see that going all four directions because it only is required in the direction where the noise receiver is. Here's another example where the rooftop unit was creating noise at the neighborhood, and the noise was from the intake and the exhaust. So the proposed solution was a barrier wall around the unit and an exhaust silencer on top, in addition to acoustic panels on the back wall, because the noise is coming from the intake on either side, so there could be some reflected noise coming off the wall as well. So that's why acoustic panels are provided that could absorb the noise.
When you do an acoustic barrier like that on the previous slide, how much static does that add to like the condenser fan section?
If the acoustic barrier wall is if it is designed to have a certain distance away from the condenser unit, you don't really impact the condenser or the intake fans. So in this instance, based on whatever the mechanical equipment supplier's recommendation, they would typically have 36 inches gap between the unit and the wall. As long as you meet that criteria, you're not really impacting it. So in this case, that's what we did. We had a 36-inch gap, so there will be very minimal or no impact to the intake fans.
I think he's asking about on the discharge jag. There's a silencer to reduce the sound from the chiller condenser fans.
Okay.
Typically, chiller or rooftop manufacturers have, I'll say, difficulty, knowing what the fan performance is. 99.9% of the units don't have any silencers or any construction on the discharge of the fan. So that's what Buck's question is. If you had an approximation of what the air pressure loss would be on the silencer.
Okay. So silencers can be designed to make the air pressure loss lower or whatever it comes out to be. And in this instance, the pressure loss was 0.25 inches of water. But we can always make the silencer so that the pressure loss is lower. Before one goes about designing this, the mechanical consideration would be one of these items. When you have a rooftop unit in front of you, we could look at the performance of the rooftop unit, have a static pressure that is available, and this way we can calculate what is allowable pressure loss before the unit will start, seeing difficulty with its performance. And that's where that will all be considered during the mechanical aspect of this project. Does that answer your question?
Yes,
yeah,
sir.
Perfect.
We got a couple of questions rolling in.
Okay.
So, does Park Lane own the PE stamped structural calculations for wind loading and uplift forces of an enclosure around the RTU? The previous slide shows what looks like an enclosure sitting on the roof and not tied into building structure.
Like this one here. Yes, this design will be PE stamped. Absolutely. And we provide something similar to this. We have done this in so many occasions in multiple locations within the States and Canada. And yes, we do provide always structural design or PE stamped or PN stamped if it is in Canada.
Okay. Next question is, for the silencers or other structures that are added, who designs the structure? Who checks to see that the HVAC unit can accommodate the additional structure attached?
Right. Typically, we do that. We will so in some instances, the weight of the silencer is so minimal that it wouldn't really impact the unit. Before one goes about designing it, we reach out to the mechanical equipment supplier and make sure that what the weight of the silencer can actually be handled by the unit itself. And if that is not the case, as you can see in this example, the silencer is actually not sitting. I know you can't see it, but it's not sitting on top of the unit. It has its own structure supporting it right beside the unit. But yes, we will be the ones who are designing the structure for something like that.
Okay, thank you.
Which will also be PE stamped. So anything structure oriented will be PE stamped, and we will also, it's the norm. All right, so here we have a in discharge silencer and an acoustic barrier, depending on what the noise source is. Here, there probably was some leakage from the bottom, and the noise through the chimney. So circular silencers were provided so that the noise coming through the chimney is, or the stack is mitigated, and at the same time, noise coming on the sides were also mitigated with the addition of the acoustic barrier wall. What the barrier wall does here is essentially just direct the noise up, and it's also an acoustic barrier, so it can absorb some of that noise. And that's pretty much what you would need in this instance. This is an example of a series of silencers that were provided for a big intake. This was a gas turbine facility or testing facility where they required huge volumes of air going into the facility and coming out. And this was done so by providing acoustic plenums underneath. So this is like a corridor where a person can walk through, but it's completely acoustic on all surfaces except on the top where it opens up into this intake. So the air comes in through the intake, goes into the plenum, and then out into the test facility. This is a very good example of what can be achieved with the multiple rows of bank silencers. Sometimes it could an enclosure can also have louvered enclosure where you have an equipment that needs to be mitigated, but it still needs air to flow in and out. Then in that case, you can just have a louvered facade, which is acoustically lined, and the enclosure itself is also acoustic. So whatever the sound coming from the pump, the compressor, it can absorb the noise, and essentially the transmission loss achieved by this enclosure will be whatever that needs to be met, dictated by the acoustic consultant. If you need any more details, please feel free to go over these links. You will see a lot of case studies that we have done in the past, and what you need to know in terms of mitigation and all that stuff. I'll be more than happy to take any questions if you guys have more questions.
Okay. We'll wait a couple minutes to see what pops up. So basically, in a nutshell, Park Lane will do the calculations, provide the solution, and return it back to the engineer so it's ready to go when they're for their building design.
With the exception of identifying the noise. So that would be the part where the acoustic consultants will come in and identify what the noise sources are, how much it needs to be mitigated. Except for that part, the rest of them we typically do.
Okay. Does anybody have any questions for Jag? What is the relationship between ductwork velocity and NC ratings?
Ductwork velocity and NC ratings. I'm not sure about ductwork velocity, but I can talk about NC ratings. NC ratings are typical for indoor noise. When you have inside, okay, let's say you have an air handling unit on the rooftop, and the air handling unit is servicing, I don't have any slides on it, so sorry, I apologize that I don't have a slide on it, but I will talk about it. The air handling unit is servicing intake air for the rooms inside, and also taking away the air from the rooms through the exhaust. Now in this case, each room, depending on what kind of room or what kind of facility it is, it will have a specific NC rating, which is dictated by OSHA, or even ASHRAE has some specific NC rating for, be it library or a gymnasium or a classroom and such. You'll have a specific NC rating that you need to meet. What an NC rating is essentially noise levels at each individual octave band spectra. And if you exceed that, then you're going up another NC level. That's the idea. And in this instance, how you would go about mitigating it, again, the noise is coming from the air handling unit. So you just stick a silencer in it, make sure that the pressure losses does not impact the performance of the air handling unit itself, and make sure that the NC rating is met at whatever the room the air is being serviced to. So that's what an NC rating is.
Well, I think the question was more like, so if you have a 24 by 24 duct and the air is traveling down that duct at a specific feet per minute, it's going to be a higher noise rating than it would be if that duct were 36 by 36 because it's more constricted. So I think the question was, how does the airflow impact or correspond to your noise criteria?
I don't believe that's how it is. The duct does the duct dimensions impacts the absorption of noise when it gets to the sound source. So where the receiver, for instance, a room is being serviced by a duct that comes from the air handling unit. The dimension of the duct is only dependent because of the fact that the absorption of the noise is it depends on the absorption based on the duct. If it is a bigger duct, then there's not a lot of, even though there's a lot of surface, there's not a lot of absorption through it. And whereas the smaller duct, it's really the property of the duct. It doesn't have anything to do with the NC rating.
Okay. We got a couple.
I'm sorry, if I can just, Joe, this is Jim O'Donnell. I can talk to you further about this. I'll just chime in my 2 cents that obviously a higher velocity versus a lower velocity could create more noise. And then also too, it's important to sort of eliminate what I'll call turbulence. And what I'm referring to is when you're transitioning from different sizes and have takeoffs and elbows and turning vanes, et cetera, like that, it's best if you can follow, SMACNA recommendations for transition sizes and degrees, et cetera, like that. So, but Joe, I can talk to you further about that. All right, thank you.
All right, a couple more questions. Are there warranty concerns from manufacturers since we are now enclosing a unit designed in an open air environment, i.e. head pressure issues, condenser air recirc, decreased unit operating efficiency?
As long as you're not, again, whenever we do the mechanical consideration for whatever rooftop equipment, we always, reach out to the equipment provider, ask them for their recommendations before we go ahead and put something on top of it. For instance, the pressure losses, only they impact the performance, but how much does it impact? It really depends on how much static the equipment has. Will that affect the warranty? Not so much. Unless it impacts the performance, it doesn't really impact the warranty of it. Even impacting performance would simply mean that the amount of air that's being serviced in, or the amount of cooling that's doing to the unit, that's the part that will be impacted. Aside from that,
that would really be the manufacturer or sales rep's job,
right?
To make sure that nothing would be a warranty violation, or
exactly
something that would cause the warranty not to be on. So, like if we were doing something like this on an Aon unit, we would have to go back to Aon applications engineering and basically get their blessing to say, yeah, this is fine.
That's exactly it. Yeah.
So it really comes down to the sales rep working with the manufacturer, and then also working with Park Lane to make sure that it's not an
it's
issue.
compliant all around. Yeah.
Okay. Can a list of installation locations be provided or accessed on the Park Lane website?
Installation locations, as in like where they were installed.
Do you have an install list? I know you have I've seen one. I know there's a lot of installations in Canada.
Right.
So Bob, I think we can get that. I think we can get something over to you.
Yeah.
And last one is, does Park Lane have the noise sources of RTU models from the typical commercial manufacturers? I usually see the sound levels as discharge, intake, and radiated. Do we need to get manufacturers to provide all the breakout points you've previously identified? Compressors, condenser fans, casing, radiated, etc.
No. So as long as we have the manufacturer, like the serial number or like a model number, we could get that from their website. They typically would have for each model what their sound, exhaust intake, and radiated noises. while we can get that information, really the acoustic consultant is the one who would typically stipulate, oh, based on this bylaw, it needs to be X dB at this property line. You know, that's something that you would have to actually measure to see if it actually complies or not comply. Most of the time, you could just, you know, if you have a unit that's, there is a simple calculation which is based out of an ISO standard that you can calculate. But typically, we recommend that an acoustic consultant takes a look at it and suggests a solution, you know, because the solution can be very simple or could be very complicated depending on what the sound source is and the location of that sound source.
So with that being said, what if you have a situation like you have a project, it's installed, it's on the roof, it's a rooftop unit on top of a penthouse.
Mm-hmm.
You know, you got $1 million penthouse and there's a makeup air unit for the whole building.
Right.
So say there's no acoustic consultant involved. How would you guys help? What would you need? Or would it be the same process? You still have to get the measurements.
You still have to get the measurements. You don't know how much to mitigate unless you know what the sound levels are at the penthouse. You know, because or else it will be a iterative process, you know, trial and error. You're just like, oh, is this mitigation good enough? No, it's not. Then you have to go back. So it's better you involve an acoustic consultant in this instance. It doesn't take a lot, you know, they're not that expensive, but they give you a very accurate estimate of what needs to be done. And this way the mitigation can be straightforward instead of being a trial and error or an iterative process. And in most cases, the penthouse issue would be because it's transmitted through the roof. Typically, in that case, it would be a vibration isolation most of the time.
All right. Well, I don't see any more questions. We can stick around for a couple minutes in case somebody has one. But Jag, you know, all things considered, thank you very much. Thought you did a great job. You know, with the technical difficulties that we had today.
I'm sure Matt would have been able to explain a lot more things, but I'm sorry that I wasn't able to get you a lot more details on some of these slides. But I hope I answered most of your questions. And I do have another separate presentation on the indoor acoustics. You know, I know the question popped out with the NC rating was this duct. I didn't quite understand back then. But when Jim explained it, I kind of got an idea what you were referring to. So if you guys ever need that, I can always, you know, present that as well.
Yeah. Well, we really appreciate your time today. And I would like to thank everyone for jumping on. Again, apologize for the technical difficulties. Won't make that mistake again. And you know, we'll be doing our next webinar in February. Jim's going to get out the notice on that. And we hope everyone has a great Christmas or Hanukkah. Enjoy your holidays. And again, thank you everybody for joining us today. We really appreciate your time.
Thank you, everyone, and happy holidays.
Yep. Thank you, Jag.
Thank you.